But now I should stop talking and leave the floor to you, Christer.
Thank you very much, Birgitta. And I'm so happy to finally be here today. It has taken a long time, a long journey. And I'm very happy to see so many people here in Sundsvall, friends, family, colleagues, previous colleagues. And I would like to welcome you all so much. And also all of you who are on Zoom, I can see how many, maybe Ingen, 40 people. Very warmly welcome to you also. So the title, Process Intensification in Mechanical Pulping. And let's see. As Birgitta said, there has been many partners in this work, not only Holmen, that has been the main sponsor, but also several other companies and universities. So thank you all that has been helping in these projects. The purpose of this work is to reduce the cost for production of mechanical pulps. And doing so by simplifying the process and thereby needing less machinery, less unit operations, and also to reduce the electrical energy demand, which is the variable cost. Simplifying the process would also affect fixed costs, and that is means that it's easier to maintain and operate a simplified process. And of course, all this together would contribute to a lower environmental impact, which is very important today, I think. So back to the title, Process Intensification in Mechanical Pulping. Process intensification is a method of doing development that was developed within the chemical process industry during the last 2 decades of the 20th century. And the central parts of process intensifications include that you try to combine more than one function in an equipment using smart catalysts, more precise chemical reactions that would contribute to higher yield and less byproducts. And process intensification should lead to large steps or improvements in terms of the amount of equipment, capital cost, less raw materials used, less energy, and less waste. In my work, I have focused on 2 of these aspects to reduce the amount of equipment and to reduce the energy consumption. Back again to the title, Mechanical Pulping. I'm very happy to have some non-mechanical pulping friends here, my neighbors, my family, good friends, and they're not experts like many of you are. So just a few words about mechanical pulping. It's actually fairly simple. You take a piece of wood, in this case, spruce. You make sure that it is humid or moist enough with some water. You heat it up. You can add some chemicals, but just a drop. And if you put more, then it's chemical pulp. But we use sometimes small amounts of chemicals. And finally, you heat it. You apply mechanical energy. And by combining these 4 ingredients, and of course, it is very important which kind of wood you take, which piece of wood. So that is also an important factor. But if you have a certain wood, and I have worked with spruce, you can combine these 4 factors and make very large differences in the pulp quality and in the fibers produced. And you need a lot of energy, which has been over the years one of the drawbacks with mechanical pulping, even though one big advantage with mechanical pulping is that you have a high yield. Over 96% of the wood becomes paper or board. Just to give you who are not familiar, some kind of feeling for how much energy you need in mechanical pulping. If you would take an electric car, drive around the globe, if there were bridges over the oceans, that would consume roughly 6,000 kilowatt hours. And it would take you 400 hours in 100 kilometers an hour. That amount of energy would produce 3 tons of pulp. And on the paper machine, it will take 2-3 minutes to consume that amount of pulp. So as you can realize, it's enormous amount of energy that is used. And the consumers of the energy, in this case, are our refiners. You can use other machines also to produce mechanical pulp, but I have worked with refiners. Large grinders, quite similar to what you made flour from seeds like 4,000 years ago. With you have barred patterns that crush the chips and produce free fibers. The main products that you use mechanical pulps for are printing paper and paperboard. And these products, they demand very different kind of fibers. For printing papers, you want to have slender fibers that make a good paper sheet with nice surfaces. And when you make paperboard and put mechanical pulp in the middle, you want it to be bulky. And I have in this work only worked with printing paper, but I am quite convinced, maybe we can discuss more, that this can also be applied for integrated board production. Okay, so the research question that I have worked with is, how should a process for mechanical pulp production be designed and operated to increase the energy efficiency and to attain sufficiently developed fibers and fines with a reduced number of unit operations? And there are 3 sub-questions in this work connected to the main question. That is, what refining conditions are needed to enable a level of fiber development in a single stage refiner such that no or only little more development is needed to attain final pulp quality? Second, how and to what degree can low consistency refining be used in a simplified TMP process? And how should a process be designed to make it possible to omit screening and rejects treatment? So this is the focus of this work. A TMP, or a mechanical pulping process for printing paper, looks something like this. Of course, there are large variations, but this setup is quite common. And the process consists of 4 main parts: preconditioning, when you have the watering and the fire, heating and moisturizing; mainline, the main refining, separating and developing fibers; screening, removing poorly developed fibers and unseparated fibers, chives; and rejects refining. So what I have tried to do is to take away this, or remove this last part of the process with the screening and the reject line, remaining then only the preconditioning and mainline. And very little work has been done over over the years in this direction. Usually, actually, processes has tended to become more and more complicated rather than more and more simplified. So I wanted to be able to produce a pulp that corresponds to what you use for newsprint. Not so popular anymore, but still in some use. My wife, she loves to read them in the mornings. So still some newsprint production, but not much. But that's only to have some kind of goal chosen with newsprint. I have worked all the time with large scale equipment, mill equipment. It has been only Norway spruce, but again, I think this could be applied for other raw materials. No paperboard, as I said, and I have not included any aspects of bleaching of the pulp. Yes, as I said, I've been working in the mills, and Birgitta mentioned Braviken, the Holmen mill, where I have done most of the trials, but I have also worked with Holmen Hallstad mill and Stora Enso Kvarnsveden. And the work has been made over, as I said, over quite a long time, and by successive changes in the mills, by investing in new machinery, rebuilding, new piping, quite a lot of new pipes, especially in Braviken, I would say. And then we have sampled from the refiners, from the process, and done standard laboratory analysis. In 2 of the studies, I have made more detailed fiber analysis together with Rita, for instance, and some other colleagues to really investigate how the fibers are affected with this when you simplify the process. And then 2 of the processes that I have investigated have been actually run all the way to the paper machine. And this nowadays, where a yellow newsprint is from one of the full-scale trials where we produce paper and printed in normal printing. So those of you that are present here in Sundsvall and are really nerds, you can come and have a look in the break. I have used quite a lot of different methods or approaches to accomplish this work, which includes pre-treatment, chip pre-treatment with impressor finer. Addition, as I said, only a small drop of chemicals. So we have used low dosages of sulfite, below 1%, usually 0.5%. I have evaluated different kind of high consistency refiners with different rotational speeds, the highest RTS refiners in Hallstavik, and also increased speed refiner in Kvarnsveden, the CD 1800. I have compared 2-stage and single-stage refining. We have tried different segment designs, the grinding surfaces, and also tested a new developed center plate for the double disc refiners. Improved production rate, which has been quite impressive, I would say, especially for the DD refiners, going from when we started this work, 10 tons an hour up to 18 tons an hour per machine. Increased refining temperature, which means increasing the pressure in the machine. And finally, I have also studied quite a lot low consistency refining in different positions in combination with different pulps. So these are some of the processes, the major ones studied. You can find it if you forget any of the abbreviations used on the figure number 28 in the thesis. You can go back to this if you wonder what is this. And so this includes the chip pre-treatments, the high consistency refinings, and different combinations with low consistency refiners. And a base reference for this is a two-stage single disk refining. And detailed fiber morphology has been investigated for these processes. And these two processes has been evaluated on paper machines, where I will focus on this trial. So back to the process scheme of TMP refining. And actually this process looks quite similar to what we have in Hallstavik, with two-stage single disk refining, low consistency refining, reject system, reject refining. So such processes requires around 2,000 kilowatt hours per ton in refining energy, plus all the energy around with pumps and presses and you name it. So there is another 250 kilowatt hours per ton roughly. So you could say for the best processes today, you need some 2,000 kilowatt hours per ton in total specific energy. It's a good number to have in your mind, 2,000 kilowatt hours per ton. So I wanted to remove this part and improve the efficiency of the mainline refining. Now over to some of the results. And as a baseline reference for this work, was or is the pulp line that it's no more in operation in Braviken in this configuration, but it was when we started. And that was used to produce newsprint and looked quite similar to this one, with, again, two-stage single disk refining and high plus low consistency refining on the reject. And in the figures, you will see squared symbols from primary and secondary stage pulp and the final pulp. So this red dot is the most important reference in this case, the pulp going to the paper machine to produce standard newsprint. I also have included in the more detailed fiber analysis an improved reference, still single disk refining, but in this case, twin 60 refiners, two-stage LC refining followed by screening, where the reject goes back to, the screen reject goes back to LC. And hydrocyclone reject is refined in high consistency refining. And again, there are 2 points, 2 black points in figures from the second stage and the final pulp. So in the results, I will show mainly when it comes to energy, tensile index, when you tear, pull a strip of paper apart to measure how much energy you need to break the paper. And you have specific refining energy. So here are the base reference, first stage pulp, second stage and final pulp, and the improved reference. And I have also here included a best available technology reference that we evaluated different pulp lines in Scandinavia. Tensile index was measured on rapid curtain handsheets, and you who are familiar with tensile index, this means that normally the values of the rapid curtain handsheets is higher tensile index. So you have some 8 units. So this would be some 42 to 44 with normal handsheets. It's good to keep in mind. I will show some ISO handsheets also. So as you realized, there was a lot of different processes and quite a mess. Not so easy. And I will not try to explain. It will take the whole night to go through this in detail. So I will try to condense it. Again, the reference pulps to keep an eye on, and some symbols also with single disc, double disc refiners, round, RTS, and CD refiners. And then the different lines here also have different meanings with refining curves, high consistency refining, LC refining, and reject systems. And points that are filled yellow has been, there has been sulfite added to the process. And the dashed outline, we have done chip pretreatment with impressive finer. So keep an eye on the red spot. And that is what we want to attain. So from this quite large amount of data, since I want to improve the energy efficiency, it has to be pulps that give good strength properties at low energy. So there is not so many processes that gives a good fit, in this case, giving low energy consumption at a high enough tensile strength. And again, if you look at chives content, that is very important. It's not so many processes that really gave low enough chives content corresponding to the final pulps here. And the conclusion from this initial, just looking at the data, is that you need to have high intensity refining, which is RTS, the yellow diamond here, or double disc. The other points are double disc pulps, different configurations. So the squared processes are 4, and that is the RTS in Hallsta, where we added sulfite before the second stage refiner. Single stage DD refining was evaluated in the Kvarnsveden mill. Impressive finer chip pre-treatment with sulfite addition, and DD refining with or without LC refining after. And finally, the last paper, or second last paper, paper 6, includes a trial with a process where sulfite was added to the chips right before the refiner. No impressive finer chip pretreatment. The refining was running at high production rate and with high housing pressure, which is high temperature, followed by 2-stage LC refining. Quite similar production rates in all these processes. So let's look at more details in terms of the energy efficiency. And when I talk about energy efficiency here, this is meaning that reducing the specific energy to a given tensile index. It's not so easy to define energy efficiency for mechanical pulping. Rita Fritius and Olof Fritius and I have written a paper on that if you're interested to dig a little bit more into energy efficiency. But reduced specific energy to a given tensile index. And when you look at the different high consistency refiners evaluated in this work, you can see that the high intensity refiners, DD, double disc, and RTS, they require some 300 kilowatt hours per ton lower specific energy. This is well known and is verified by this work. And you can also see the same change in specific energy at increased production rate here from the SD refining here at higher production rate compared to this and this point, the double disc. And production rate, in this case, shown here first by the double discs going from 11 to 15 tons an hour, and single disc refiners from 13 to some 17 tons an hour. So it has also some 300 kilowatt hours per ton. This is also known from earlier work. Sulfite, if you add it in the process, what we have seen is for every kilo of sulfite that we add, you gain some 30 kilowatt hours per ton in specific energy. And we have been using somewhere usually between 5 and 10 kilos per ton. So when you combine double disk refining with impressive finer chip pretreatment, here you can see the process, and double disk refining, you reduce the specific energy with some 300 kilowatt hours per ton. And RTS refining gives some similar specific energy. Then another concept that I will come back more to is the trials we did to the paper machine when this was produced. And that process was, as I said, chip pretreatment, double disk refining, and LC refining. And with that, compared to the BAT process, it was around 400 kilowatt hours per ton, lower specific energy. And finally, looking at the last process, with the double disk refining, high temperature sulfite, high production rate, two-stage LC refining, it is 900 kilowatt hours per ton lower compared to this base reference, and 500 kilowatt hours per ton compared to the compared to the BAT process here. And I would say this is on a diagram like this, it looks okay, but I would say this is quite unique. 20 years ago, no one would have believed that it was possible to produce a tensile index of final pulp with less than 1,300 kilowatt hours per ton. That is less than what we had in the primary stage refiners in Braviken when I started. So it's quite amazing, actually. And I never thought myself that that would be possible. Another conclusion from this, looking at energy efficiency, comparing double disk refining, here is a refining curve made in one of the double disks in Braviken, and LC refining, you can see that it's similar slopes. In and out LC refiner or adding more energy in a double disk gives the same slope. And most work studying LC refining has compared that to this kind of single disk refiners. And then the LC refiners looks more efficient, but not when you compare to double disk refining, or RTS have also high slopes. So summing up, high intensity refining is important to reduce the energy consumption. Sulfite adds to it, increased production rate, high refining temperature, and LC refining all contribute to reduced energy consumption. And what is new knowledge, I mean, all these pieces have been studied before, but to my knowledge, this has never been combined, all these aspects, all these approaches at the same time in full scale. And as I said, producing newsprint final pulp at 1,300 kilowatt hours per ton, I have never seen in full scale. And also this with the efficiency of LC refining, we have seen that in some cases it is similar to high consistency refining. So I will take the chance to answer the first, put the first question. Well, Christer, this looks quite good, but are you sure that you have not forgotten any important process? That was a good question. Well, of course, I have not studied all processes, and just one idea could be to improve the RTS refining. We have not been able to do so much rebuilds in Hallstavik and RTS refiners, but I think there are opportunities to also look at single stage RTS refining with some kind of pre-treatment. So yes, there can be more efficient processes, but the ones we have studied are mill scale, which is quite important. Now over to pulp quality. And first, looking at some of the pulps with the optical property, light scattering coefficient, that contributes to making the paper brighter. And also when you read it, you don't want to see the back page, only the front page. So then it's important with a high light scattering. Double disc refining gives, without any chemicals or anything, gives the highest light scattering. And this has been shown before. Nothing new, actually. What I have seen in all the work with low consistency refining is, and here are only 2 examples shown, but it's always so that we don't increase the light scattering over LC refining. I will come back to that. And also sulfite reduces the light scattering, so you can compare here and here. So some loss in light scattering when you add sulfite to the process. There are 2 a little bit strange points in this figure, and that's the last trial we did that is included in the thesis, where we compared the 2-stage single disc improved reference and this double disc configuration. And they should be higher, and I can't answer why. This point should have been somewhere here on the white, together with the white points here, other single discs, and this one should probably higher. And luckily we did some trials or some analysis of these pulps also in both in Kvarnsveden and the Valmet laboratory. And if you look at data from both those laboratories, so you can see here the trial pulps, they are on the level that is for normal newsprint, I would say. So something was strange with the rapid curtain sheets when we did the evaluation in Braviken. So the conclusion is that this process can deliver, the most efficient process can deliver light scattering that is as similar to newsprint. It was even a little bit higher, as you can see, compared to the reference pulp. Yes. Fiber length. All the high intensity processes produced lower fiber length, pulps with lower fiber length. This is also known from the literature, and we have seen the same thing, always lower fiber length. What is interesting is that the 2 paper machine trials that we did are the 2 circled pulps here, and they are have among the lowest fiber lengths. And even if there was low fiber length compared to single disc pulps up here, the paper machine runnability was perfect, no problem, no breaks in the printing. So, and I hope we can discuss that a little bit more also, how important is fiber length. Okay, but now we have shown tensile index, light scattering, Shives content is okay. You can produce a pulp similar to final pulp. But if you go a little bit deeper and look at the fiber morphology, how does it look with the simplified processes? When you do printing papers, you have to have strong enough paper and you have to have smooth surfaces. To attain that, the fibers has to be flexible so that they conform in the sheets. And you also have to have a certain amount of fines, small particles that contributes to both strength and optical properties. So a piece of wood, this is a 1 year ring of spruce wood, direction of growth here. And if we make a close-up and compare that to a printing paper, this is a magazine paper from Hallstavik, you can see that there is quite different form of the fibers. So we want to go from this hollow structure to something that collapses and gives good surface. And as you can see, the thickness of the papers it's just 2 or 3 fibers, uncollapsed fibers in thickness. So it's very important to get the fibers to collapse and to have flexible, good bonding fibers. So is this possible to attain with the process without the reject part? And to evaluate that, I took out pulps from the reference process in Braviken and from this double disc configuration. Sample points that you will see in the diagrams again are here from after the single discs and final pulp, and right after double discs and after low consistency refining. I also have included some data from a project, or this is from paper 5, and where Rita and some other people were involved very much. And we compared pulps from CD refiner and LC in Kvarnsveden, DDLC in Kvarnsveden, and the RTS line in Hallsta. And in that trial, we took out 2 levels, pulps at 2 levels of specific energy in the high consistency refining. And at the lower energy, we took out pulp after the low consistency refiner. So 3 points for every process. So first, let's look at external fibrillation and cell wall thickness. It's important to have thin fiber walls to make the fibers to collapse. And here we have fiber wall thickness measured on scanning electron microscopy pictures. And PFI helped us with that. And here we have fibrillation index, and that was measured with FL is Fibre Lab. That was measured in the Fibre Lab in Kvarnsveden. So it's an optical measurement of the fibrillation. And what you can see here is that high intensity refining, the highest intensities with the RTS and the double discs gives the highest level of external fibrillation. CD refining, 1800 RPM, a little bit lower, but still higher than the single disc pulp from Braviken. The extreme double disc pulp with the sulfite, high temperature, high production rate is somewhere in between here. So this extreme conditions seems to have reduced the level of external fibrillation, but still higher than the reference. Now also looking at another important property of the fibers, and that is the bonding ability and also conformability, how they form in the sheet. And that was measured on, in this case, on the 3 pulps. That is reference, the double discs, and 1 double discs in Kvarnsveden operating at 15 tons an hour. So just 1 stage double disc refining. And here it is density measured on the produced hand sheets of the fiber fraction. So fines were removed to measure only the properties of the fiber fraction. And that is plotted against Z strength, also of the fiber fraction. So you pull the paper not along, but in the Z direction of the paper. And that is an indication of the bonding, and density an indication of the conformability of the fibers. And what you can see here is the final pulp of the reference and the simplified process. They are very close, both in density and in Z strength. The highest Z strength as a measure of the bonding ability was attained with the single stage DD refining without any sulfite. But still, it looks like you can attain the same bonding ability with a simplified process. Finally, I had one slide just to show you that all the Shives measurements previously shown was optical analyzer, and they tend to miss large single Shives. So we measured that also in this trial, and you can see that they are quite close, a little bit higher Shive content with a simplified process, but this is still lower value than what we had when we used the Somerville fractionator to measure the Shives content. The final pulps in Braviken was around 0.15 in Shives content, and this is around 0.1. So still better than most final pulps also measured with Somerville. What you can also see is that the reduction over the LC refiner is lower than what you have over the reject system in the reference process. And this implies that it's very important to have a low, if you use LC refining only after high consistency refining, you have to have very low Shives content already from the high consistency refiners. So what's new in this? Well, this work has shown that it is possible to develop fibers with only mainline refining and reach the same degree of conformability, bonding ability as a process that includes normal screen fractionation and reject refining. I have used low consistency refining quite a lot in this work, so I wanted to show you some special issues around that. And this is since low consistency refining has been used quite often lately, or say the last 20, 25 years to improve the energy efficiency. And we have several installed both in Hallstavik and Braviken, and also, as I mentioned, in Kvarnsveden. So in this investigation, that's paper 5, we had the RTS refiner and the 2 refiners from Kvarnsveden, and we measured internal fibrillation, not external. External fibrillation is the threads going out from the fiber, but you can also have internal fibrillation, which is micro cracks in the fiber wall. And you can measure that with the staining technology. And what we saw from this study was that there was a large difference in LC refining and the CD refining, applying more energy in the CD compared to adding LC refining. It looked like the LC refining was considerably better, and that had been shown in another investigation, not done by us earlier. But what we saw in this investigation is when you compare low consistency refining to high intensity refining, double disc and RTS, they are quite similar. So this has not been pointed out before. Yes. Then you can also see, and here are the amount of, not actually fines, but smaller particles, mostly fines, and the light scattering coefficient of these 3 pulps. And what you can see here is that over the LC refining from here to here, there are very small changes in both fines content and in light scattering. So obviously there is a difference here between the two high and low consistency refinings. Also, there is a difference when it comes to how the form of the fibers. Usually when the fibers come out from a refiner, there are more or less a little bit kinks and curls. And when you put the pulp through an LC refiner, you always reduce the curl, which almost always leads to increased tensile index just by making the fibers straighter, they conform better, densify more, and you increase the tensile index. So this seems to be an important aspect of low consistency refining, that the fibers are straightened. Whereas in high consistency refiner, usually the fibers become more curly. Not for the CD, but I included an arrow here showing some data from Rita from an earlier study on the same refiner. And in that study, there was also a slight increase in curl over the CD refiner. So this is a big difference in the two refining technologies. So summing up LC refining, we have clearly different fiber development in these two machine types. Less peeling of fiber walls in LC refining. Fiber curl is reduced in LC refining, whereas it increases in high consistency. Internal fibrillation is higher for LC refining compared to CD and single disc, and the single disc refers to an other study that we did not, that I mentioned. But it is similar, the fibrillation is, internal fibrillation is similar to DD and RTS refining. And this means that less fines is created in LC refining. You get lower light scattering, low external, increase in external fibrillation, lower increase in Z strength, which limits the share of applied specific refining energy that you can have for printing papers. And what we see, and my opinion is that maybe somewhere 100 to 200 kilowatt hours per ton in LC is the upper limit. If you start to put in more energy, you lose too much light scattering. And also, again, it's preferable to combine LC refining with high intensity refining. That gives a good fiber development before LC. Okay, so now over to the paper machine trial. Finally, and there was two configurations, as I said, evaluated, and this paper was made with this configuration: chip pre-treatment with sulfite, DD refining, LC refining. And that is that point in this efficiency graph. So we consumed some 1400 kilowatt hours per ton to produce that pulp, and 100 kilowatt hours per ton auxiliary energy. And compared to this pulp, around 2,200 plus 250 kilowatt hours per ton auxiliary energy. And the properties that we produced here are pulp properties and paper properties. And what you can see is that even though the freeness of the pulp is higher for this extreme simplified process, the air permeance, which is important for printing paper, is lower, and the roughness is lower, but the tearing strength is clearly lower with this. But even if the tear strength was lower, as I said, there was no runnability problem. And you can see the reason to the low tear strength, lower fiber length. So, and this has been a big issue, I would say, in the mechanical pulping industry, focusing on fiber length. And I would say that clearly fiber length is not the most important factor to make a good printing paper. There is something more, I can't say what, but obviously with this short fiber double disc pulp, it was possible to produce good printing paper. And that would be interesting to dig a little bit more into. So finally, conclusions. Back to the research question. Yes, the process can be simplified. And it requires only single stage high consistency refining, followed by a little bit more, if you want, LC refining. Appropriate pulp quality can be attained, and you get very good fiber development as good fiber development in a simplified process as in the more complex normal. This can be made with less than 1,500 kilowatt hours per ton, total specific energy. And the sub-questions, what refining conditions are needed to achieve this? And we have seen that this can be attained with a single stage high intensity refining. And important parameters to attain that is to operate at high production rate, a low dose of sulfite, and high refining temperature. All are beneficial for the improved efficiency and the pulp quality. How much LC refining can we use? Well, obviously, there are limitations. Mainly, I would say that low consistency refining can contribute to increase the production rate in a TMP line. And by that, especially if you have high intensity refining, as I showed, there is not much difference in efficiency. If you have a double disc refiner, back it off to have higher freeness, and then you do LC refining, you come back to the same point. You have not saved any energy. But if you increase the production rate, and then put LC refining, the total efficiency will be improved. And it's preferable to combine low consistency refining with high consistency refining. And finally, how should a process be designed to make it possible to omit screening, reject treatment? And well, there seems to be several options that fulfill this, and the highest efficiency was attained with this process. Then the other ones were quite similar, I would say, but they gave somewhat different, and this needed only 1,300 kilowatt hours per ton refining energy. And well, there's reduced light scattering, increasing fiber length for these three. So it depends on what pulp quality you want to have in the end. So going from this to that process. This process has roughly 19 unit operations. And if you exclude this whole reject treatment and design a process like this, you only need 11 unit operations. And also this kind of simplified process has higher availability because there is less equipment, and it's much easier to control because there are not so much steps in the process. I think we will skip this and see if we have time to discuss some more new knowledge from this work. So I just wanted to say that it's very important to continue the research in this area with the process intensification. Maybe the suppliers of the steel doesn't like this, but for us in the industry, we for sure want to make as efficient processes with as little equipment as possible. And in the overall, this is good for the environment to use as little resources as possible. And I must say, I have not shown that, but we had, it was a big surprise for all in Braviken when we changed from single disk to double disk refiners. And the experience and the realization that you can produce paper with short fibers with good quality. So I'll skip that. So thank you very much. And finally, I just want to thank all the people that has been involved in this work. And there is a lot of people. And I would especially want to thank Olle Lindeberg. Please, just, he has been enormous help in this work. He knows every pipe, every valve, everything in Braviken mill. Without his help, this would have not been possible. Thank you very much.
Thank you, Christer, so much for a very nice presentation. And now we will have a short break. I think we will resume here in the room and in the meeting at 4:10, 10 past 4. And then we will listen to the discussion on the thesis. Bra, Christer.